Hello everyone, this is Dr. Jacob from Jacob's Lab. Today I'll be talking to you about the synthesis of methylenomycin B and analogues. This is a continuation of my earlier video titled Synthesis of 2,3-disubstituted cyclopentenones. So now we will go to the main slide of this, and I will show you the structure and isolation of methylenomycin B. Isolation of methylenomycin B, as published in the Journal of Antibiotics in 1974, they isolated this methylenomycins A and B. The two new antibiotics were found in the culture filtrate of Streptomyces, and this was found to be A and B exhibited activities against gram-positive and gram-negative bacteria, and especially against Proteus. So with the antibiotic being isolated, natural product isolated, the next intention for the scientists were to make the lab, in other words, synthesize this and show the structure is correct. So a variety of people, a variety of chemists started working on this project a couple of years after the structure was elucidated. It continued for nearly 3 decades. Many syntheses have been published. So as you can see, the structure is relatively simple with cyclopentenone, 2,3-disubstituted pentenone with an exocyclic double bond. But what is interesting is that even though it is very simple structure, it's kind of deceptively simple structure, because the exocyclic double bond makes the cyclopentenone susceptible to degradation with even weak base and weak acid. So one has to really come up with a good synthesis of this compound. So we were interested in cyclopentenones obtained from the alpha chlorobeta gamma unsaturated ketones, and fortunately we came upon this synthesis quite by chance, because we were reacting the lithium enolate of this, for example, in the 4-chlorodimethyl-hexenone, we were reacting it with some nucleophiles, and also with we are reacting with electrophiles, and also we were interested in cyclization to give the cyclopentenones. While working on that, we found that when you add benzene sulfonyl chloride to this anion of this ketone, we end up working after workup, we isolated the cyclopentenone with the benzene sulfonate on the alpha carbon next to the carbonyl group. So we extended this and we published a paper in Journal Chemical Society, Perkin Communication. As you can see, the abstract is shown here. So it's a convergent synthesis of methylenomycin B and analogues via selenium-assisted cyclopentenylation, Journal Chemical Society, Perkin Transaction, 1991. So I will go through the synthesis details in a minute. Before that, I also want to mention that I was invited to write a chapter on the Chemistry of Antibiotics, Volume 2 book by Dr. Gabor Lucas of Paris, France, the CNRS director, after he saw my article in Journal Organic Chemistry and Journal Chemical Society Perkin. So I did write a chapter on this antibiotic book, mentioning, pointing out the synthetic efforts for the last 3 decades after the isolation of the Streptomyces strain. And in the synthesis, I have outlined all the synthesis, including my own work. So if you take a look at this chapter in this book, you can get more information on all the other synthesis, and you can compare it with this synthesis. To my knowledge, this synthesis is the shortest of methylenomycin of date. It may not be the most cost effective, but it is the shortest of all syntheses known. For example, we could make this antibiotic in 1 day. In the course of 9 hours, I could make it, a few grams. So That is the beauty of this synthesis. You see here all the chapters of that, all the sections in that chapter, you see different antibiotics, and methylenomycin is just one of them. Synthetic approach to methylenomycin. So you can, this is a very interesting book which you should read it cover to cover. Now, novel selenium assisted cyclopentadienylation. That is the paragraph I abstracted from the textbook. We call it Matthew selenium assisted cyclopentadienylation. So I have the honor of putting my own name as the title of the last name, and my own last name as the title of this reaction. So it is a selenium assisted cyclopentadienylation because the cyclopentene ring, pentanone ring, is created with the selenium on it. So essentially, selenium is important for this cyclization to proceed and to continue with the synthesis of methylenomycin. So as you can see, the details are given, the abstract of the experimental is given here, and you see that the methylenomycin is obtained in 96% yield in the last step. In other words, the hydrogen peroxide oxidation and elimination of selenium, phenylselenic oxide, and the liberation of methylenomycin proceeds in 96% yield. But the yield before that is 80 and 70%. So the overall yield still from the basic starting material, from the basic unsaturated ketone, you get the product in 3 steps in 35% overall yield, which is really not a bad, which is considered decent yield for a natural product. Now, you see that this slide shows exactly what is happening here. In other words, it is showing you how we made this thing. In other words, as you can see the title, alpha chloro beta gamma unsaturated ketones that is required for this methylenomycin synthesis. So you can see that the R groups, R, R1, are different. Methyl is constant. Me on the beta carbon of the unsaturated ketone is constant. So if you have R1, for example, as methyl, you see the product will also methyl. If R1 is just, if R1 in the left side is H, the product R1 is also H. When R is methyl and R1 is ethyl, you get R1 as ethyl. So then when R is benzyl and R1 is H, you do get R in the benzyl R1H. So in other words, the benzyl group is attached to the carbon when which chlorine is attached. So these are the 4 different unsaturated ketones, the chloroketones that we synthesized. Now in the next slide, you will see how the reaction proceeds. After you make a alpha chloro-unsaturated ketone, it is treated with LDA, lithium diisopropamide in THF at -70, and you generate the anion, and the anion is alkylated with phenylselenium chloride. And that gives you the selenium cyclopentanone. You see, it proceeds through a intramolecular, in simple terms, to explain it, it proceeds through the anion here, attacking here, proceeds to a SN2 prime, eliminate chlorine, you have this. That's a simple mechanism. Now, this intermediate, on treatment with LDA, lithium diisopropamide THF again, you get an anion again, but this time you have selenium enol. It's a enol flanked by selenium, and this can be reacted with allyl bromide at -78 to give this product in 80% yield, and this on oxidation gives the methylenomycin analog with 97% yield. Now this is unique because this is methylenomycin. It's one step more complicated than methylenomycin. You have introduced another group. This type of methylenomycins are not being made. There is no literature precedence for anything remotely close to this. As you can see, this is probably the only way you can make it, because to reduce a double bond here, as it is difficult unless you proceed through this selenium chemistry. This is the only solution so far, unless we invent another reaction. So anyway, that is this one. Now you can make methylenomycin by alkylating this intermediate with methyl iodide. And then you do the selenium oxide, hydrogen peroxide oxidation. You form the selenium oxide elimination and the double bond is formed here. So that introduces methylenomycin. So that again, that proceeds in 96% yield, the last, the oxidation step. So I have shown you two analogues of methylenomycin. Now, this is 4 analogues I made of this methylenomycin by selenium oxide elimination. As you can see, the selenium cyclopentenones, I introduced hydrogen peroxide, gives you 91 to 96% yield of the 4 are substituted cyclopentenone with the double bond, exocyclic double bond. So these are all analogues of methylenomycins. So you see R and R1, when R and R1 are methyl, you get, and R2 is H, you do get the 96% yield of product 18, in which we have methylenomycin. In other words, the exocyclic double bond has both hydrogens. It's a vinylic. So that is parent compound. In the slide, in the chart, in the table, the second entry, when methyl is, R is methyl, R1 is ethyl, and R2 is going to be methyl. Because you see, you get a methyl substituent on the methylenomycin. In other words, methylenomycin has hydrogen, not R2. R2 is hydrogen in methylenomycin, but in this compound, compound 19, the second entry, has methylenomycin, methyl substituted, 93% yield. Then you go to slide 3, entry 3, you have R1. R1 is still methyl. R is methyl, R is benzyl. So that is benzyl, and R1 is methyl. So that gives you, on oxidation, R2 is hydrogen then. R2 is hydrogen. So that gives methylenomycin, except instead of the methyl group, you have a benzyl group. So it's methylenomycin without the methyl group, but with the benzyl, which makes it a little bit more stable because of the benzyl group. It's highly conjugated with the benzyl group. So that compound could be very interesting to test also, this analog. But so far we haven't done testing on any of this. Now the entry 4 is the most interesting, is that when R is methyl and R1 is allyl, which we showed earlier how this allyl group is introduced by alkylation. That will result in R2 being extended. R2 is another allylic conjugation. As you can see earlier, you saw the conjugated, doubly conjugated exocyclic bond. This compound, 21, of course, obtained again in 95% yield, is really worth trying. It's expected to be more active than methylenomycin based on all the literature analogues that I have seen, except nobody has synthesized anything remotely close to the exocyclic double bond, extended exocyclic double bond. There is no literature report. Nobody has synthesized. So it's a novel compound. We have also filed a patent on the whole scheme, including the composition of matter for the last compound. Methylenomycin, of course, it's a known compound. So the next slide, I am showing you the mechanistic pathway. This is the first mechanism that comes to mind. It's cyclization of the lithium enolate may involve intramolecular SN2. But it's not a simple SN2 prime. It involves selenium, because selenium forms a selenium ylide. As you can see, once the enolate is formed, the enolate is formed in the first step. The enolate reacts with phenylselenium bromide to get a selenium enolate, and then the selenium can form an ylide by electron shift. The electrons of selenium and go in and move out, eliminate this. And therefore, the selenium ylide, now we have a triene system, the selenium so-called ylide can cyclize. So in other words, it can go like this. Corn, it's a corn cyclization. Concerted, Woodward, it satisfies Woodward rule because it's a concerted. This is probably the way it is happening, because according to Woodward's rule, this is the most favorable. So electrons move and selenium gets its electron, the double bond shift, the double bonds are all considered. So that Kohn rearrangement gives the intermediate, probably goes through this intermediate, although you could mention it's a direct considered reaction to give this. Either one, whether it goes through the Kohn to the cyclopropanone, vinyl cyclopropanone rearrangement, or directly, both gives the same product. The question is, the vinyl cyclopropene rearrangement is well known, and even the ylide reactions are known. But in this case, since nobody has done a SN2 prime to generate isocyclopropanone, cyclopentanone, we have to do further study to establish the actual reaction pathway. So these three pathways are just basic, suggestions by other chemists. So in my case, I am proposing a intramolecular SN2 cyclization, simple SN2 cyclization with the help of selenium as the driving force. That gives the product. Very easy to explain it. However, there is one more. When I published this article in the Journal Chemical Society and Journal Organic Chemistry, one of the referees suggested a new mechanism. He is involving an SN2 prime attack of diisopropylamine. Instead of using anything like what I did or what the others did, instead of the vinyl cyclopropanone rearrangement, he is suggesting that isopropylamine that is used can add in a SN2 way, SN2 prime way to generate this intermediate. So now you see the anion is here, it shifted everything. So this can, which closes in SO-text manner resulting in the product. So that this is again kinetically favored. This will also cyclize directly to give the cyclopentanone. In other words, the movement of electrons should be like this. It comes here and this nitrogen gets the electrons back. So the enolate attacks here and it's just an SN2 displacement. So first SN2 prime, secondly SN2 displace the nitrogen. So that's the third mechanism. And with that I come to the, I believe the end of the slides. I mentioned about this compound earlier, this extended conjugated methylenomycin B. No such compounds exist in the literature up to now. So this is expected to be more reactive and more active, biologically active than methylenomycin. Now, the methylenomycin B, the original methylenomycin B. However, we do not know the toxicity. This needs to be tested. This is going to be very interesting in cancer research because nowadays a lot of research is going on this kind of binding to the cancer site, extremely conjugated systems. This is an extremely conjugated system on both ends. So such in the mechanism of cancer treatment, they're doing a lot of work, especially the Nobel laureate from Caltech and Berkeley are working on actually reactions on the cell of the cancer patient. So these compounds could serve its purpose. So anyone interested in testing this in the lab, in vivo or in vitro, I will be able to make 99% pure plus